Hey, good morning, everybody. My name is Bob Stankovitz. I'm here at the San Diego Supercomputer Center, and I'm the director of Exceed's ECSS project. I'd like to welcome everybody to the March ECSS Symposium. Excuse my voice, I'm on the tail end of a cold, so I'm just still not quite sounding right. We're going to get started in just a minute here. We've got two great speakers lined up. So we have Richard Lawrence from Texas A&M University, supporting HPC research and education with Open OnDemand. And that's going to be followed by Rajesh Kalyanam at Purdue University, Anvil, a national composable advanced computing resource for the future of science and engineering. I want to remind everybody that this is an Exceed event, so we are governed by the Exceed Code of Conduct. I will take this link and I will paste it into the chat in just a minute so that you could all take a look at that. Oh yeah, we have the whole code of conduct here. I think it's a little bit much to read in real time. So again, I will post that in the chat. And sorry, we don't need that anymore. That's an old slide. So I talked to the speakers beforehand about questions. So for our first speaker, for Richard, he was a little unsure of the duration of the talk, so we're going to hold questions until the end. Rajesh said that he can take questions during the talk. So I'll ask that you either raise your hand or you type your question into the chat, and I'll field them for the speakers. So let me give it just about 30 more seconds. I see a few more people trickling in. And in the meantime, Richard, if you want to go ahead and put your slides up. All right, so we're at 10:03, so I think we will dive in. It looks like attendance has kind of leveled off. So Richard, whenever you're ready, go ahead.
Howdy, my name is Richard. I'm a user support specialist at Texas A&M University in the High Performance Research Computing Group. I'm here to tell you about the Open OnDemand framework, and in particular, some examples of what you can do in that framework by showing you what we here at A&M have done. Hopefully this will help you to understand the value of using Open OnDemand, the value that it provides to researchers. So in this, I like to divide all my talks into sections, even if they're not too long. So in this talk, I will tell you why it's important to have something like Open OnDemand. I'll show you what Open OnDemand is generally, and then I'll show you what we have done with it at A&M. Finally, I'll describe what I believe the next steps are for us at A&M in order to provide even more value to researchers, and then always there's a conclusion. So the introduction, trying to motivate what's important about this talk, and so the state of the field. Cyber infrastructure is challenging. Infrastructure means, of course, hardware, but it also means things like managing software packages, managing user accounts. There's an entire ecosystem, and for a researcher just getting started, it's overwhelming. So any way to ease the transition for a beginning researcher into high performance computing is of great value. Next, we know that researchers are preferring graphical environments. So that would be the IDEs, the integrated development environments, and the corresponding analysis tools that are graphical. Sometimes you can have one tool that does both of those jobs. And finally, science increasingly requires sophisticated software practices. So here's some acronyms to throw at you. It basically means we need to be responsible for our software, our data, our communication with other researchers, and having good practices in place enables all of that. So we want to educate researchers about those practices so that science can move forward into the future properly. So here's an example of an IDE. This is the Jupyter Notebook. If you are familiar with Python, then this will be familiar, but it's not important that it is Python or that you're familiar with it. The point here is that whenever you're developing Python code or any code, researchers prefer to be able to click buttons. So this interface has lots of buttons. You can see here there's a run button for executing code. There's a file button for saving files. Coding on the command line has moved into the past, and so we need to be envisioning something like this whenever we're planning for the researcher's needs. Another example of a technology is containers. So containers are a way to make software portable. There are several container runtimes in use. Docker is the most popular. Singularity is an alternative to Docker that is appropriate for high performance computing. Charlie Cloud, a recent development similar to Singularity, is an alternative to Docker that's appropriate for high performance computing. Many scientific packages have already been containerized, so you may recognize some. There's probably more you're not aware of. Containers are kind of infiltrating the back end of everybody's stuff. Even if you don't know you're using containers, you might be using containers because they are so much easier than the traditional way of doing things that it's pretty clear that containers will be affecting everyone in the future. So I've got a diagram here to explain vaguely how containers work. The developer's operating system exists. The developer writes their software, then they bundle it up in the container, and you basically just copy that container whole onto the target operating system for deployment. Then it interacts with any local data that's on the target system. And so you can get running with very minimal understanding of how to install or build software. That's the point of it. And one more thing to say about the state of the field. Research workflows are bigger than really any of us anticipated. When we're at HPC, we think, oh, people come here to use our machines because we have, lots of powerful machines. But really, the research workflow is continuously evolving. You have researchers doing learning. They're learning their programming languages. Development, they're debugging why their code doesn't work. Production, obviously, they're enjoying their coffee while the machines do the work. And then analysis, someone has to take a look at the result of those computations and try to understand what it means. And then you go back to the beginning. So the research workflow for the researcher includes all these steps and more. So if we want to be able to support all of these steps so the researchers can continuously do their work with the best tools that are available. If the researcher wants to adopt some new technology, like the Python IDE or the container that I showed you, we have to make it so that they can understand how that fits into all of these stages. Because once they get to a stage where they don't understand how the technology fits in, they will abandon it and go back to the old way of doing things. And that's a major barrier to researchers trying out the new tools and the new best practices that we want them to have. So the next section is Open on Demand. I will tell you what this framework is and how we use it to do the things I've been trying to describe. So Open on Demand is the web interface for HPC. Basically, it's a web service that runs on a node somewhere in the cluster, and then people off campus, if they wish, can use their browser to access that web service. click buttons and get access to the HPC resources. So browsers, researchers love this strategy because it reduces complexity for them. They don't have to do SSH style syntax to get to their resources. It allows them to click on buttons instead of typing. It allows us to present more beautiful forward face to the researcher, so that you know, they can enjoy the power of graphics or even just good web design, which is not really available on the command line. Open OnDemand is, of course, a community, an open source community. So they have a web page, openondemand.org, and mostly it's a group of HPC sites like ourselves that share with each other what we're working on and try to develop a common framework that you know, the next site can install and get started hopefully as quickly as possible. So here at Texas A&M, we have an instance of Open OnDemand, which we named the HPRC portal. That's the name of the website that the user navigates to in their browser to get access to the HPC resources. The web page is, of course, customized per site. It's not uniform across all of Open OnDemand. So here you see that our instance has the maroon color, which is our school color here at Texas A&M. And this is generally understood that whenever you want to install Open OnDemand on a cluster, the first thing you do is customize it to match the look of your institution. So we'll just take a closer look at one of these menus. This is the interactive apps menu. Each of these, and if this was a real web page, you would scroll down, but there's like 30 or so items in this menu where you can click on it and it will lead you through some forms, and you can get access to graphical software that will be running on a compute node. So it connects the researcher in their browser at home to a compute node through some graphical interface, so they can use the HPC resources in the way that they're comfortable. And this is basically the meat of why Open OnDemand is so important. But of course, Open OnDemand can do some other things. So if you're in the stage of research where you're wanting to submit batch jobs, then Open OnDemand has a form for you to submit your batch jobs. This form basically acts like the sbatch command for Slurm if your site is using Slurm. Of course, Open OnDemand supports other schedulers as well. But here at A&M, we use Slurm. So if you have already written your batch script, then you can submit lots of copies of it to our scheduler using forms like this. Although it is convenient because it reduces one element of the command line, this is for someone who has already written their batch file. It doesn't really help you if you don't know how to write a batch file in the first place. So next, here's a feature called the View Only VNC link. So VNC is an example of one of those interactive apps. It basically gives you a desktop to launch generic graphical software. And here's an example where someone wanted to launch Chimera so they could look at some proteins. And you would click this blue button on the left to actually get to the desktop to do your work. But if you wanted to share what you were doing with someone else without literally giving them remote control of your desktop, this other button over here, View Only, basically acts as kind of a Zoom screen share, but there's no Zoom, it's just all in your web browser. So an example of usefulness for this feature is if you're teaching a class in how to do some HPC task. For example, maybe you're teaching your chemistry students how to use a molecule simulator, and you want to be able to give them feedback on if they're doing it correctly. You can have them share, the students will share their view-only link to the teacher, then the teacher can see what the student is doing live and provide that feedback, but without introducing the complexity of remote control access to the desktop. The next thing we're going to look at, here's an example of a form that you might fill out to get access to a Jupyter Notebook. So this is a default looking form, not the one we have at A&M, but maybe a more vanilla version if you just installed Open On Demand and haven't customized much yet. So it basically just has a few options for your batch scheduler. So your batch scheduler can decide how much resources you will need to do your Python development. The problem with this form is that it doesn't really have any options for what kind of Python is going to be provided in that Jupyter IDE. Most Python users are not just using vanilla Python. Python is a package-based language. So as soon as you want to go beyond basic into advanced, you need to start installing packages, and therefore the user needs to be aware of what packages they are requesting, and this form doesn't know how to handle that. So that's a good segue into the next section, quality of life improvements in Texas A&M's Open On Demand portal. I will now show you some things that we have done at A&M to improve quality of life for our researchers so they can get more value out of the Open On Demand. So this is the dashboard. Well, the dashboard is called two things. Maybe one of them should get a different name. This is the one that we have built to show the users the facts about the batch scheduling. So whether the nodes are currently under heavy use, so they can plan if it's a good time to submit jobs, how many service units they have, which is our measure of accounting for their jobs, and then a disk quota, which is we have disk quota due to the choice of file systems that we have. So then users can plan if they have enough disk space to install software or if they need to ask for help. The next thing that we have developed is the job composer. The job composer is different than that job submit page that I showed you, because this one is designed for someone who does not know how to write a batch script. Instead, it has form fields that correspond to the scheduler parameters. In our case, it's Slurm. So the user can read and figure out how to answer the question of how much resources does their job need. Then this form translates that into the language of the scheduler. So your first batch job ever might, for example, come from a form like this, where it helps you decide what the relevant parameters are for your job. And the last thing down here, this field is the module field. At Texas A&M, we use the LMOD module management system for keeping track of many different but similar installations of software. So if users still need older versions of software, it's still on disk and they can have it. The caveat is they have to know that they need to specify which versions of their softwares they need. So this module field helps out with that because it can auto-complete versions of software that are known to exist on our system, which reduces, one possible method of failure of mistyping the version of the software. This next feature, this is two features I put on one slide. So the quota request and the help request. A couple of slides ago, I showed you the dashboard with the file quota information. On that page, there's also the button that takes you to this form, which is the one that says, I don't have enough space in my file system to install my software or whatever, then I need to ask for more space. And because asking for more space, the procedure depends on how much space you need, and it depends on whether you're a PI. The form has some intelligence to it to guide you through kind of a flow chart to answer the questions that are relevant to the user. So that way, when we get our quota request in our ticketing system, it is already pre-populated with the information that we need to properly process the request, which is an improvement for us, because if the user doesn't know which questions they need to answer, then we have to manually tell them which questions they need to answer each and every time they want to request help. And that is an expensive time that we enjoy having to go through less of. So over here we have create help ticket, which is a similar philosophy, reminding the users that they need to describe their problem in detail reduces the amount that we need to come back and ask them questions about their problem in order to properly understand their problem. So having a form that says, oh, why don't you tell us about the job ID, because the user will have forgotten to tell you the job ID, then reminding them to provide that means we have a better chance to be helpful on the first try. So here we have the Jupyter Environments menu, and this addresses the specific concern that I mentioned before with the vanilla looking Jupyter Notebook form, in that it didn't have any way to specify what kind of Python environment the user needs. So we developed a way for the user to specify what kind of environment they need. So the first item here is a drop-down menu. In this case, I have selected the module load, which corresponds to the LMOD software management system that I described earlier. So in that case, if the user needs to use Python software that we are providing and managing through the LMOD system, then they can select which module in the following drop-down menu after that one. So with just a couple of clicks, they get access to any software that is known to exist on our system. And of course, the other parameters with the batch things are there. They're just off screen. I just took the screenshot of the part that's relevant for this discussion. Since containers are an important part of the future, it's worth a moment to talk about them here. Containers are an option for the Jupyter environment form that allow the user to, instead of specify a module, here they specify the path to an image file for their container. If you're not familiar with containers, that's not a big deal. The point is that we have made it so that supporting containers is just as intuitive for the user as supporting the previous way of handling software that we were supporting. So what I'm trying to do is encourage the user to say, you can make containers part of your regular workflow where you do your development, you do your analysis, and containers are with you every step of the way. So in this particular example, I picked a container image that was provided by NVIDIA. So NVIDIA develops a version of TensorFlow that works with the GPU. So if the user wants to use TensorFlow with GPUs, then they can choose to use NVIDIA's variant of that instead, and it will run pretty fast because NVIDIA knows how to use their own GPUs. Now, in terms of the back end, supporting containers is really not that difficult. So if there was a line of code in the back end that said Jupyter Notebook as a shell command, then you would simply have to insert, prepend the corresponding container syntax. The container syntax here at Texas A&M is singularity path to image file. And then here we just have some symbols because the open on demand happens to be in the language of Ruby on Rails. That's not important. You don't need to know a lot about Ruby on Rails, just that the very minimal change to support containers here suggests that it's worth our time to do that. As a case study, I used this form to teach containers to students. So the course agenda involved a bunch of topics, one of which was, here's how to use containers. And the example is using TensorFlow with the GPU through the on-demand portal interactively. Therefore, as the researchers were becoming familiar with what containers are, they also saw that it was possible to integrate that into their existing workflow. In fact, the Jupyter Notebook that I showed you at the beginning is the exact Jupyter Notebook. That's the one I used to demonstrate containers. It all comes together. Nice. So far I've taught this course 3 times. Attendance has been increasing as researchers become more comfortable with the idea of learning containers from the HPRC, but still relatively new. So I hope to increase that as we go forward by providing more support. It looks like on my clock, I'm running a little low on time. If there aren't too many questions, then I can launch into the 4th section, which is my vision for the future, what I would like to do next. If there are lots of questions, then perhaps we could skip that and just field questions instead.
So Richard, there were a few questions that were answered along the lines, but if you want to answer one, it's in the chat now by Jonathan Scone.
Where are users building containers in your? That is an excellent question, which is one that I was going to address on a slide in section 4. So that would be a reason to proceed and talk and go through section 4. Are they released? David asks, and the answer is not yet. We intend to wrap up our developments and put them in a GitHub and make them accessible, but we haven't quite finished with that yet. So hopefully someday they will be released. Podman is another example of a container technology we're not using here at Texas A&M, but I'm certain someone is using it. And similarly to Singularity, it would be easy to support that in Open On Demand. I would like to go into the section 4, even though we are low on time, because one of the slides helps to answer a question. So the way that Open On Demand is structured, currently at A&M, we have different pages with forms to fill out for different types of jobs. So here on the left, we have our job composer, which I showed you. That's helpful if you want a quick job, but you don't know how. We have the job template method, which I showed you before, which is the more vanilla method. That is helpful if you already have a batch script and you want to launch lots of copies of it. Finally, we have that form for launching the interactive Jupyter Notebook job, which connects you to a node on the cluster. But all these forms are completely separate from each other on the back end. And so one of the things I would like to do is try to unify them so that on the back end, the common elements are not repeated across multiple forms, which reduces the maintenance work for the administrators, because as supporting new software is always evolving, you shouldn't have to be making similar changes in multiple places across the back end to support new software. We would like to make it so that the researcher can seamlessly move from one type of job to the other and get a similar experience. So for the module method of supporting software packages, one of the things that users do is create a virtual environment to install their packages in. We would like researchers to do this, but doing it on the command line is clunky. I noticed that some people who are doing this at home have a graphical solution for installing Python packages. So it makes sense that at HPC, we should also be able to do that. And here, for containers, this is kind of answering the question I saw in chat. Pulling or building a container image is a task that we want research to be utilizing. But with the command line method, it's clunky. And what I mean by that is because specifically container tasks are resource intense, here at Texas A&M, we don't allow that on the login node. You are required to get a compute node and do your container pull, container build activities on the compute node. So the extra step of going from a login node to a compute node and then doing the command line syntax is just clunky enough that I feel it would be of a benefit to the researchers to develop a graphical way around this, so that the researchers click on some forms, and then as a result of clicking on those forms, the container pull and build operations occur on the compute node. So every opportunity that we can give the researchers to move away from using the command line will help them to feel more comfortable adopting containers in the first place if they were on the fence to begin with. So the conclusions, just to review, is that education, teaching researchers how to use the new technology, and the research itself using that technology have a natural synergy if the user interface is good. And if the user interface is graphical, then it reduces the barrier to entry for new technologies such as Python language or containers for new researchers. And so we would like to improve the quality of research by supporting those technologies, and therefore it's important to provide user-friendly interfaces for those technologies. Acknowledgements, of course, we gratefully acknowledge the support of the National Science Foundation for numerous awards that fund our activities here at the High Performance Research Computing Group at Texas A&M. So here are some recent NSF award numbers. And that is the end of my presentation. Let's see if there are any more questions that we have time for.
Great, thank you, Richard. There is one question here, but let me just ask you to answer that one through the chat, so we.
All right, I will respond to that in chat, and the next presenter can get ready.
Great, thank you, Richard. So Rajesh, whenever you're ready.
Let me just start sharing. Right. Does that look good?
Looks good.
Awesome. Well, thanks everyone, and thanks Richard for that great talk. That was really interesting. I was looking forward to hearing more details on the quality of life improvements. That was really helpful. This one's going to be slightly different. It's a lot more high level than the details that Richard was just presenting. This is an overview of the new Anvil system that's joined the Exceed pool that's now deployed at Purdue. So I'll be giving a really high-level overview of Anvil, the different kinds of workloads we support, and some, I guess, data from our early user program that just concluded a couple of months back, and our plans for the future. So my name is Rajesh Kalyanam. I'm a research scientist at Purdue University and also one of the co-PIs of Anvil. There's quite a lot of representation from the research computing team here in this meeting, so I'm going to be leaning on several of them to answer any questions that I can't handle. So Anvil was deployed, or I guess designed in response to this ACSS solicitation from NSF in 2019, and there were two categories in this solicitation. The first was capacity systems that are intended to essentially increase the capacity and offer more computing SUs to Exceed users. The second category was innovative testbeds for the more modern new workloads, and Anvil was proposed under the first category as a capacity system and then funded in 2020. We've been deploying Anvil, doing a few of the initial things that were necessary. So deployment, early user benchmarking and testing, and also the NSF acceptance review. And I'm happy to say that we passed through all of those, and then we are now officially in production, which started in February of this year, and we'll be operating for 5 years starting now. So at its core, since it's a capacity system, obviously there's a huge compute cluster, and this has state-of-the-art CPU and GPU nodes. The CPU portion will be delivering close to 1 billion CPU core hours per year to exceed. Complementing that, and with sort of a nod towards the more modern workloads with gateways and non-traditional applications, there's also a composable subsystem that'll support container deployments and gateway applications. As far as the software goes, so in addition to the traditional HPC software that many of you are familiar with, there's also the interactive computing environments that Richard was just describing. And so we have a lot of those on Anvil as well, which are again intended to reduce the barrier to entry for users who are new to HPC. And through our production operations, we are also going to be having a lot of training and workforce development activities so that people who are new to HPC can get trained in using these resources, and also the next generation workforce can be trained in both operating their own HPC center and also supporting these applications in the future. So I'll touch a little on the design principles behind Anvil. So the system design was really motivated by looking at the kinds of jobs that we saw in Exceed in the past. As you can see here, a majority of the jobs that were not on the flagship at that time, the Stampede 2 clusters, used fewer than 128 cores for the period between 2017 and 2019. And so that drives our decision to use 128 core AMD nodes. And again, a large majority of the workloads, 84% specifically, used no more than 1,024 cores. And so that'll fit within 8 nodes of Anvil or fewer, and that drives essentially a rack and IB configuration, and also some of the restrictions in our job queues. Diving a little deeper into the actual Anvil system. So again, the capacity portion of this comes from 1,000 compute nodes. These are all 128 core AMD EPYC processor based nodes. This is the new AMD Milan processor, which is the current generation. And totally, we expect close to around 5.1 petaflops peak performance. We'll be running our HPL run soon, so we'll know more then, but this is our anticipated peak performance. As far as the machine learning workflows go, we have GPU nodes. So we have 16 GPU nodes. Each of them have 4 NVIDIA A100 GPUs, which are again the newer version compared to the previous B100 generation. And there are also 32 large memory nodes, each of which have 1 terabyte of RAM. So these are designed for more of the big data kinds of applications. The composable subsystem that I mentioned before, it is comprised of 8 large memory nodes and a bunch of storage nodes. Since these are intended to support gateway applications, so we will be using Kubernetes for orchestrating these containers and supporting application deployment. So in addition to the command line, we also have Rancher, which is essentially a web interface for container orchestration and for access to the different Kubernetes features. We also have plans for cloud busting to Azure. The specific tasks are still in the works, but essentially we will support both expanding the HPC job submission queues to Azure, but also support machine learning workflows to use some of the toolkits that are present on Azure, the SDKs, so that researchers who have Azure credits can span between on-prem and cloud resources. And finally, as far as storage goes, we have multi-tier storage with both ZFS and GPFS. And we have 10 petabytes of the parallel file system and 3 petabytes of all flash. We also have support for Globus, so you can transfer data between both your campus resources, but also other Exceed systems. The software stack, this is pretty familiar, I'm sure, to most of you. So all the usual suspects as far as programming libraries and compilers go, including GNU, Intel, and AOCC compilers, because this is an AMD system, as well as various flavors of MPI. We also have several debugging and profiling tools that you can use to monitor your applications. As far as scientific applications go, again, most of the general purpose math and statistics libraries, but also really specific, domain-specific application libraries like LAMPS or NAMD or things like that. Containers, again, Richard talked about these. So we also do support Singularity-based containerization and execution on Anvil, and several of the domain-specific applications also leverage Singularity containers to be able to support these modern applications as part of the module system. We also have the whole data sets directory that'll be mounted into all the nodes, and it'll provide access to databases like the NCBI database for bioinformatics applications. As far as the machine learning and data science support goes, so as I mentioned before, this is primarily based on the hardware of 16 nodes with 4 A100 GPUs, so 64 GPUs in total. On top of that, the software layer is comprised of the HPC SDK from NVIDIA and all the popular machine learning libraries like PyTorch and TensorFlow. All of the software, again, uses LMOD and the module system. And so most of these can be loaded on just by using module commands. NGC containers is one thing that we are now supporting on Anvil. So these are out-of-the-box optimized libraries and also pre-trained models in several machine learning domains like NLP or bioinformatics, which NVIDIA has a whole catalog of, and we have some of those loaded onto Anvil as Singularity containers that can, again, just be loaded using the module system. But then you can also pull in containers from the NVIDIA catalog and run them for your own applications. And of course, as Richard mentioned, Jupyter really reduces the barrier to entry for users getting into HPC systems. And so on Anvil as well, you can use Jupyter as your interactive computing environment to get access to both the CPU nodes, but the GPU nodes as well, and all of these module systems. Again, I won't delve too deep on this slide because Richard just mentioned this. Anvil also supports Open OnDemand, and you can see most of the things that he presented, the Job Manager and Composer. Our Open OnDemand is considerably more vanilla, so it doesn't have some of the quality of life extensions that Richard has developed. But again, it supports different interactive scientific applications, both Jupyter and RStudio. So in addition to OnDemand, we also have support for ThinLink, which is a remote desktop tool that you can use to get a VNC session into your login nodes, either from the web browser, but then ThinLink also has a desktop client that you can use to get a whole Linux desktop environment onto your login nodes, and then you can run a variety of graphical applications on there, or you can even submit jobs to the compute queue from the terminal inside that VNC window. I'll touch a little on the composable subsystem itself. So many of you may also be familiar with this. So the new modern workloads are not just HPC, but there's increasing need for gateway style applications. Researchers may just need to have a gateway that has a scientific code on there to share with others, or they may want to have the gateway as really a science gateway to the HPC system behind the scenes. And so in order to support these workloads, we now have a composable subsystem on Anvil that allows you to provision on-demand resources, CPU or GPU and other resources, and then deploy your science gateway applications on top of that. So these can range from things like, say, Jupyter Notebooks that are deployed in the application mode, or more complex science gateway frameworks like HubZero. It can also have things like data processing pipelines. So we have a few applications that may want to have a long-running RabbitMQ message queue that's running on this platform and then ingesting messages from elsewhere into a database. And so the composable subsystem is really designed to support these modern workloads. And all of this is made a little easier through our support for ranchers. So essentially the workflow that someone who wants to use this would go through is either come with the publicly available Docker container images. So there's a lot of images out there for things like MongoDB, different kinds of databases, different kinds of web servers like Apache or Tomcat, or they could build their own Docker images, and then they would then push this to either the public registry or a private registry that we host. We would then pull in those container images and then orchestrate them and deploy them. And then finally, they can also leverage things like monitoring through Prometheus to see what kinds of resources the containers are using, to see if they need to scale it up or increase the resources for their particular application. And people who are familiar with Kubernetes, they can just use the command line kubectl utilities to orchestrate these applications. But we also have Rancher, which is really a web interface to these different features of Kubernetes that allows you to set up namespaces, set up deployments, set up services all through a web browser. You can just click and select options to either get a static IP and a host name and all of that. And all of that happens pretty easily through this web application interface available in Rancher.
Rajesh, we have one question came in the chat.
Sure.
This is from Jonathan Stone. Is there composability of the network to guarantee quality of service?
So I think the network is connected to the various national networks to sort of guarantee some basic level of throughput. I don't know if there's really composability in there. And I don't know if anyone else from the team wants to chip in there, but I don't think there's really composability in that sense. It's just connected to the various national networks like the Science DMZ and all of the others. So I think that's essentially how we would guarantee quality of service. And I don't know if anyone else wants to chip in there. Yeah, up there, this came in. I think there was there's another question from Jonathan there. Request. Okay, so I think maybe the question is on the composable subsystem itself. So composability here is just the nodes, the compute, and the disk and the storage, not really the network. So it would just mean how many CPU cores, how much of memory, and how much of disk storage you want to use. So say you were deploying a database which needed high availability, then depending on the number of cores you needed for that, you would be able to select that and deploy it to have that level of high availability. So essentially, it's using pieces of the nodes that form the Kubernetes subsystem. And I hope that answers your question, Jonathan. Let me just move on while I wait for any further questions in the chat. So just switching back to the HPC system and job submission, there's several job queues which are essentially Slurm partitions. On Anvil, they can support different kinds of workloads. As you can see here, I won't go too deep into this, but there are some queues that allow you to run across a whole rack. For example, the wide queue allows you to run jobs across 56 nodes, which form one rack on Anvil. And then there's separate queues for GPU, for the GPU nodes as well. The charging factor on Anvil is based on the number of cores, CPU cores your job is using, or the number of GPUs being used. Some of these partitions are node exclusive, like the standard and wide, so they would charge for the entire node, which is 128 cores. And one service unit on Anvil, which is the standard exceed, charging calculation is one CPU core for 1 hour or one GPU for 1 hour. And of course, some of these these partitions here apply their own charge factors, so there may be a scaling of 4, for example, in the large memory nodes. Let's see if there is. Okay, there's just Kevin responding. All right. As far as the storage systems goes, like I mentioned before, we have GPFS, which is backing the Scratch system on Anvil. There's different storage portions that the user can use. Obviously, the home directory, a standard directory for all the applications, and then there's Scratch and projects directory that they can use to either store temporary files during their jobs or to share files across their whole allocation group. Some of these are backed up, as you can see here, based on the snapshot schedules. Others are not really backed up, and then they're purged after a certain period. All of the documentation for Anvil can be found here on this webpage, and I think one of our colleagues can maybe put that in the chat. So you can find different pieces of information, like how you submit jobs, the usual Slurm directives that you need to provide, and also a list of all the software that's there and ways to load the different modules. I'll end with just a brief description of the early user program and some of the results so far. So here's a recap of our timeline. We We were deploying Anvil through fall 2021, did our benchmarking and early user evaluation then. In Jan of this year, we completed our acceptance review with NSF and then opened up to more general startup education, but also campus champion allocations. And through spring, now we're in production, like I mentioned before, and we'll be ramping up all of our training and outreach activities. Let's see, is there another question in there? Thanks. So in November and December of last year, we did our early user period. We had 24 groups that ended up submitting jobs and using the system, which totaled nearly 145,000 jobs. And in terms of our SUs used during this period, it was close to 10 million CPU core hours and 43,000 GPU hours. And just some of the responses we got were really positive. Many of our early users really saw very good performance with the A100 GPUs. And also the use of NGC containers in particular helped them get up and running really quickly because they could just load the container and start running their workloads without having to load modules and compile their code and all of that. Down here at the bottom, I have some more feedback on some of the specific scientific workflows that were carried out in Anvil. So particularly bioinformatics workflows took less time than other systems, again, due to the A100 GPUs and the GPFS file system performance. One of our early users was able to do this really long time scale GAN-D simulation with a speed up compared to other Exceed systems. And like I mentioned before, the NGC containers and the A100 GPUs really help, I think, speed up performance of many popular MD simulations as well. Quick note on the application performance, since this was, I think, one of the newer Exceed systems that were using these newer generation AMD and A100 GPUs. I won't go too deep into these graphs, but you can see here there's results from single node benchmarking, multi-node scaling here at the bottom, and the GPU results. So our performance benchmarking did, I think, follow the trends that we were expecting, comparing the Milan on Anvil here in gray and the single node results here with the Rome, which is the previous generation of AMD CPUs. And here at the bottom is the V100 to A100 comparison. As you can see, it did have a much better performance with A100, but maybe not quite to the level of the DGX systems at some other centers. Finally, so we are plugged in completely into the Exceed allocation process. And so each quarter we will be offering 250 million CPU SUs and 125K GPU SUs. Our startup limits are pegged at 100K for CPU and 1,000 for GPU, which we hope will be sufficient for researchers who want to just benchmark their applications and try some of these newer architectures that are now available. And with that, I want to thank you all for attending this talk. And there's our email address for Anvil, which you can send emails to if you have any questions on the system. Thank you.
Great. Thank you, Rajesh, for that really nice overview of Anvil. I see that we have a hand up. I'm just going to make a couple comments first. So first of all, congratulations on passing your NSF review. We've been through a few of these, and now it could be quite a beast. So congrats on that. And I just have one question before I turn it over the floor. The cloud bursting feature, is that something that's available widely
not yet.
To everybody, or is it?
Yeah, we have done some experiments with that. So I think we were thinking of it for several different use cases. One was to just, if you say had a deadline and you really wanted to span both systems and get your jobs running quicker, then that's one option. The other option really is the SDKs that are there on Azure. I think some of those are really good for the training phase, for the model training phase. But I think to answer your more specific question, I mean, so we don't really provide SUs on Azure, so you have to come with your own cloud credits. But if you wanted to span workloads between on-prem and cloud, then that's something we could support. If you wanted to do your training on Azure and then run those models here on Anvil, then that's something we would support as well. But again, that's still in the works. But for certain, you would have to have cloud credits coming in, so we wouldn't really provide that.
Okay, great. thank you. And I have a question here from Sudhakar. So go ahead.
Hey, thanks, Rajesh. Very nice. A couple of questions. So one is, so you described some benchmark applications and so on. Can we assume they're all available from your, whatever /apps space?
Yeah.
The kind of a related question is, are there any other licensed applications? I mean, so these are all looks like they're all more open.
Yeah, they're all open. Yeah.
Are there any licensed applications that you support on Anvil?
Yeah.
Like
Yeah, so
Gaussian, for example,
yeah, these are all available. We especially the WARF, I think we weren't sure initially, but then we had to run some benchmarking for WARF, and I think we found that we could. So we use SPAC for managing all of the software. So I think we were able to get WARF to build using SPAC. So these obviously, I mean, they're the usual suspects. They're all available. As far as licensed software goes, we don't really provide site licenses. I know some other centers do that. We have people who have come in with their own VASP licenses, so that is something that we will surely support. If it's Quantum Espresso, I think we can support that as well. For Gaussian, we tried to talk to them to figure out if we could get that deployed. I don't think that really worked out for us, so I don't think we support Gaussian at the moment. We do support VASP and Quantum Espresso.
Okay. The other question is for these composable systems. Do you have any interface to request those systems, and how quickly would they be available?
Yeah, so the composable right now it's not part of the allocation process. So what we decided is anyone who has a regular allocation can just get the composable for free. I mean, we haven't had a lot of takers for that yet. I think eventually, when we have a lot of people using it, we might think of an SU model and how to allocate that resource. But for now, anyone who has a regular allocation can just get it for free. If you're a campus champion, obviously, you can also get it just for free.
Thanks.
So do we have any other any other questions for our speaker?
Hi, I'm Lisa Perez, A&M. Hi, Rajesh.
Hi,
I have
Lisa.
a quick question about, I saw on your Open OnDemand portal snapshot that you had windows available.
Yeah.
How did you manage?
So I should say that some of this was us cheating. We don't, I mean, so this particular screenshot is not really of Anvil. It is, as you can see, it says Brown Compute Desktop. So that's one of our campus clusters. We do support Windows on there. I think Steve is on here, so he knows more about how we did that. I think it's, yeah, Steve, do you want to say anything about that? I think it's an image. I don't know what format the image is in, but I do know that we support Windows on our campus clusters. Yeah, but I should say, go ahead, Steve.
I was just going to say that I don't want to get into the gory details off the top of my head because I haven't worked on it for a little bit. But basically, we expose a Windows image running under QEMU that can be connected to over the on-demand interface.
That sounds reasonable. Thank you.
Sure.
Yeah, and we haven't figured out the licensing for its deployment on Anvil, so I think that's the reason it's probably not on Anvil yet.
Understandable also. Thank you.
Okay, so we're just about at the top of the hour. Do we have any last questions for Rajesh? All right, if not, again, thank you very much, Rajesh, for the excellent talk. I love seeing the overview of Anvil. Unfortunately, our first speaker had to leave early. Another great presentation. So the question earlier: will these slides and recordings be posted? Yes, we will. We'll be reaching out to the speakers about the slides, and the recording should be available soon. So with that, I'll let you all go, and hope to see everybody for the for the April ECSS symposium. Thank you.
Thank you.